Hello, my name is Jacob Buell. This video is about Lab 2 for the magnetic dipole of a bar magnet for the class of Physics 2212. So for an introduction to the lab, the aim of this lab experiment is to determine the comparisons between the observable distance on and off axis of the bar magnet and the magnetic field produced by the bar magnet. To accomplish this, an understanding of the Biot-Savart law is needed. The magnetic dipole model of a bar magnet, and the distance dependence formula for a bar magnet. So the Biot-Savart law can be written as the B vector, which is equal to mu naught over 4 pi times q, just the charge multiplied by the cross product of the velocity and the r hat vector over r squared. So the magnetic dipole of a bar magnet. So the magnetic field of a bar magnet points out of the North Pole and into the South Pole. So you can see on the bottom of the photo, the vector is pointing out of north and into the south. And the B vector will be equal to mu naught over 4 pi times 1 over r cubed multiplied by 3 times the dot product of the mu vector and the r hat vector multiplied by the r hat vector and minus mu. So the distance dependence formula, the magnitude of the magnet's magnetic field due to the distance away from the bar magnet is the distance dependence formula. So in it you can see the magnetic field due to the bar is equal to k times r to the power of n. And these values we'll get in the experimental calculations. So for this lab, I conducted an experiment with my phone and a bar magnet to measure the distance between the magnetometer in the phone and the bar magnet of on and off axis measurements. The system is the bar magnet while the surroundings are everything else. I then created a GlowScript model to visualize the magnetic field of the bar magnet. So for the experiment, for the on-axis part of the experiment, we'll have the system as the bar magnet and the surroundings as everything else. And the procedure was to determine the magnetic north and then use the phone magnetometer at different distances along a perpendicular meter stick to the north direction. So you can see this laid out in the photo on the left. And then for the on-axis experiment calculations, utilize the a linear regression as a part of the Excel spreadsheet given. So had data at different distances, plugged that into the spreadsheet, and got the linear regression as negative 2.8966x minus 13.8. So the n is the slope, which is negative 2.897, and then you can calculate this out to get mu, which is equal to 2.31 amps times meters squared. And then for the off-axis calculations, the system is the bar magnet, the surroundings are everything else, just like before. Procedure, move the magnetometer up and perpendicular to the bar magnet, as shown in the photo, and then the results are shown in the table at a distance of d_perp around 0.187 on average. Now for the GlowScript model, you can see I used the mu magnitude and then the distance and the GlowScript model in modeling different arrows on the perpendicular and then the on-axis of the model. So you can see in this photo here, you have the on-axis orange arrows and then the cyan blue perpendicular axis, and they point in the correct directions. So you can see I point to the right for the on-axis, and the off-axis points to the left. Because remember from the other photo, it was out of the north and into the south. So some potential errors, the magnetometer could have been inaccurate, and there could have been rounding errors. In conclusion, if I oriented the experiment to lay the meter stick at an angle with respect to the Earth's magnetic field, then the results of it would have been adjusted or skewed in the direction of north, which could have changed the values of mu and k. And if I connected two identical magnets together and repeated the experiment, and I could expect a doubling of my experimental values because of the direction of the magnetic fields will stay the same.